Something changed about the planet you are standing on. Earth is spinning faster than it has in 50 years. Days are getting shorter. Atomic clocks are drifting out of sync with the ground beneath them. Satellites are measuring it. Scientists have confirmed it. And the causes run deeper than most people have stopped to consider. Liquid iron is surging miles below your feet. Ice sheets are collapsing and physically redistributing the planet's weight. Something is happening at Earth's very center that researchers are still struggling to fully explain. We are going to cover all of it. The core, the clocks, the ice, the magnetic field, and what it means for the systems every person alive today depends on. On June 29th, 2022, something quietly historic happened. Earth completed one full rotation in less time than it ever had since scientists began measuring with atomic precision. The day was shorter than normal by 1.59 milliseconds. That sounds like nothing, a blink, a fraction so small it feels irrelevant to a living human being going about their morning. It is not. When a planet 4.5 billion years old suddenly starts rushing through its own rotation cycle faster than any recorded moment in modern scientific history, researchers pay attention. And when it happens not once, but repeatedly across multiple years in a row, the question shifts. It stops being, is this real? And it becomes, what is driving it? The answer involves nearly every major system operating on Earth simultaneously. To understand what faster spinning actually means, picture a clock. Not a digital clock on your phone, but the planet itself, turning once every 24 hours. That 24-hour day is not a fixed number. It never was. Earth's rotation has always fluctuated slightly, slowing and speeding by tiny amounts depending on forces acting on it from the inside and from the outside. For most of recorded history, the planet was gradually slowing down. Tidal friction from the moon pulls at the oceans like a brake, dragging on the rotation millisecond by millisecond across millions of years of geological time. Ancient coral fossils tell us that 400 million years ago, a year had more than 400 days in it. The days were shorter because the planet was spinning faster. Over immense stretches of time, it slowed. That long, steady deceleration became the baseline. It became the expected direction of travel for a planet moving through deep time, which is precisely why what began happening around 2016 stopped researchers cold. The trend reversed. Earth started speeding up, not dramatically, not in any way you would feel in your morning routine, but measurably, consistently. Year after year, the planet logged some of the shortest days ever recorded with modern instrumentation. 2020 set the record at the time. 2021 broke it. 2022 shattered it entirely. Here is what makes this genuinely strange beyond just the numbers. The forces that cause gradual slowing have not disappeared. The moon is still pulling. Tidal friction is still operating across every ocean basin on Earth. Something else is now pushing in the opposite direction and pushing hard enough to overcome what the moon has been doing for billions of years. That is the puzzle. And the candidates responsible for it reach from the very surface of the planet all the way down to its core. At the surface, melting ice is redistributing mass across the globe in ways that physically alter the spin. In the atmosphere, shifting pressure systems are pushing against the rotating crust. In the oceans, changing current patterns apply their own subtle drag and release. And deep underground, a churning ocean of liquid iron, more than 2,000 miles below your feet, moves in ways that couple directly to the rotation of everything above it. Each of these forces is confirmed. Each is measurable through independent instruments, operated by independent scientific institutions on multiple continents. What scientists are still working to resolve is how they interact with each other, which one is dominant right now, and whether the current acceleration is building towards something larger or approaching a natural reversal. What we know for certain is this: The planet is not behaving the way the models expected. The systems built to track time, synchronize satellites, and coordinate global infrastructure were designed around a slower Earth. They are now running behind, and the growing gap between atomic time and Earth time is forcing a decision that could have real consequences for networked systems the modern world depends on. That story starts with a single invention designed to fix a problem nobody saw coming. A millisecond feels meaningless. You cannot feel it, you cannot see it. If someone quietly stole 1 millisecond from your day, you would move through your entire life without noticing. But Earth is not a person. Earth is a system of systems, all synchronized to one another by the rhythm of rotation. And when that rhythm changes, even by a fraction of a millisecond per day, the ripple moves outward through every layer of that system. Here is the clearest way to picture what that actually means. Imagine a massive spinning wheel. Every component attached to that wheel, every gear, every linked mechanism, every device calibrated to its output, is set to turn at the same rate. Now, speed the wheel up slightly, not enough to see with the naked eye, just enough that a sensitive instrument would register the change. Nothing breaks immediately, but every connected part begins to drift out of phase with the timing it was built around. The longer the mismatch runs, the further the drift, and the further the drift extends, the more pressure builds on the connections holding everything together. Earth's rotation is that wheel. The connected systems are everything humans have constructed to depend on precise time. Consider global positioning systems first. Satellites orbit at a specific altitude and broadcast signals timed to nanosecond precision. They are synchronized to atomic time, which is anchored to the behavior of cesium atoms, not to the planet's spin. When Earth turns slightly faster, the planet's surface moves ahead of where the satellites expect it to be based on their timing. The position data shifts, not by miles, not even by feet, by centimeters. But in aviation navigation, surgical robotics, and autonomous vehicle guidance systems, centimeters matter in ways that have direct physical consequences. Financial systems represent another layer of this problem. Stock exchanges in New York, London, Tokyo, Frankfurt, and dozens of other cities execute millions of trades per second. Each transaction carries a timestamp accurate to the microsecond. Those timestamps are synchronized to coordinated universal time, which is itself anchored to atomic clocks maintained in laboratories around the world. A desynchronized planet creates a desynchronized timestamp, and in high-frequency trading environments, even a microsecond of ambiguity can represent millions of dollars of exposure and potential regulatory violation. Power grids are perhaps the most physically intuitive example of why rotational timing matters. Alternating current flows at a fixed frequency, either 50 or 60 cycles per second, depending on the country. Grid operators synchronize their systems to universal time to balance load distribution across regions. When time drifts, load balancing drifts with it. Not catastrophically, not immediately, but in ways that operators must monitor continuously and correct for. Now here is the layer most people have never been told about. All of this was already accounted for. Scientists knew Earth's rotation was imperfect and variable. That is exactly why the leap second was invented and introduced into the International Timekeeping System in 1972. Periodically, 1 extra second would be added to the official clock to keep atomic time aligned with Earth time as the planet gradually slowed. It was a patch, a small correction applied whenever the gap grew large enough to require it. 27 leap seconds have been added to the global timekeeping system since that mechanism began. Not one has ever been removed. The planet was always slowing, which meant atomic clocks always ran slightly ahead, which meant the fix was always to add time to the official record. Now the planet is speeding up. Atomic clocks are falling behind Earth for the first time in the history of the system. And for the first time, the discussion has shifted to removing a second from the official clock rather than adding one. That is called a negative leap second, and it has never been done before. The technical problem with a negative leap second is significant. When a positive leap second is added, systems that cannot process the extra second gracefully simply stall for that moment and restart from the corrected time. Inelegant, but manageable. When a second is removed, the clock jumps forward. Systems expecting to count every second in sequence find 1 second simply absent. For distributed networks that maintain state based on sequential time, that jump can cause 2 events that happened at different times to appear simultaneous, or cause a process that started at one timestamp to appear to end before it began. In certain database architectures, this breaks fundamental logic assumptions that the software was built on. The 2012 edition of a positive leap second caused partial outages in multiple major internet platforms. A negative leap second, which would represent a far more disruptive event for network systems, has no real-world precedent to learn from. Engineers can model it, they can test it in isolated environments, but until it happens globally, the full cascade of effects across interconnected infrastructure remains partially unknown. This is why the international community has been debating eliminating the leap second system entirely and simply allowing the 2 timescales to drift apart indefinitely until the divergence reaches a threshold large enough to address in a single large correction decades from now. That proposal has supporters and opponents for different technical reasons, and as of the most recent international timekeeping conferences, no final global consensus has been locked in permanently. The problem sits unresolved because the planet is not cooperating with the assumptions the system was built on. To understand why any of this is happening at the depth it requires, you need to leave the surface entirely and travel down, not a few miles, not to the deepest mine shaft or ocean trench. You need to travel nearly 2,000 miles into the interior of the planet, past the mantle, past the boundary where solid rock gives way to something that behaves more like an ocean than a geological layer. You need to reach the outer core. Earth's interior is layered like an onion, but the layers are not passive, they are active, they are in constant motion, and that motion is one of the primary drivers of almost everything unusual happening at the surface right now. Starting from the outside and moving inward, the structure is roughly as follows. The crust is the thin outermost layer we live on. Under the continents, it ranges from about 20 to 70 kilometers thick. Under the ocean floors, it is thinner, sometimes just 5 to 10 kilometers. Below the crust lies the mantle, a massive zone of semi-solid rock under enormous pressure that behaves like a solid on short timescales but flows like an extremely viscous fluid over geological time. The mantle extends roughly to a depth of about 2,900 kilometers. Below the mantle lies the outer core. This is not rock. This is not even something that behaves like rock under any conditions you could apply at the surface. The outer core is a vast ocean of liquid iron and nickel, churning under pressures and temperatures that would vaporize anything humans have ever constructed. It extends from about 2,900 kilometers depth down to roughly 5,100 kilometers. Below that sits the inner core, a solid sphere of iron approximately 1,200 kilometers in radius, roughly the size of the moon. These 2 core regions, the liquid outer and the solid inner, are not isolated from each other or from the rest of the planet. They are coupled, they exchange heat, they exchange momentum, they interact through electromagnetic forces generated by the motion of electrically conductive liquid metal, and they interact with the mantle and crust above them in ways that take decades and centuries to fully play out, which means changes happening now are the result of processes that began far earlier than any measurement record we have. The outer core's churning is not random. It is organized by the planet's rotation into large convection cells, patterns of rising and falling metal driven by temperature differences between the core mantle boundary and the interior of the outer core itself. This organized convection is what generates Earth's magnetic field through a process called the geodynamo. The liquid metal moving through the existing magnetic field generates electrical currents. Those currents reinforce and sustain the field. The field, in turn, shapes the motion of the conductive fluid. The whole system is self-sustaining and self-organizing, but it is not static. It evolves, it shifts, and when the circulation patterns in the outer core change, the magnetic field changes with them. Those changes in the magnetic field can be detected at the surface, and they reveal something about the dynamics of the outer core that no instrument can measure directly, because no instrument can survive anywhere near that depth or temperature. The magnetic field is the outer core's fingerprint at the surface, and right now, that fingerprint is changing. Since the early 1900s, when systematic global magnetic measurements became possible, the overall strength of Earth's magnetic field has been declining. Not uniformly, not at a consistent rate, but across the whole planet, the field has weakened by roughly 9 to 10% over roughly the last 150 years of careful measurement. 9 to 10% sounds modest. But the field is not just declining everywhere equally, it is declining faster in certain regions, and one region in particular has attracted the most scientific attention. The South Atlantic anomaly is a region centered roughly over South America and the South Atlantic Ocean, where Earth's magnetic field is measurably weaker than everywhere else at the same latitude. It is not new. It has been observed since at least the 1500s, when Portuguese navigators first noticed compass irregularities in those waters. But it has been expanding, it has been deepening. And at its center, the field intensity is now weak enough that satellites passing over it are exposed to increased radiation from the Van Allen belts, which normally hold at higher altitudes where the field is strong enough to contain them. The South Atlantic anomaly is the surface expression of something happening in the outer core beneath it. In the region of the core mantle boundary below the anomaly, the magnetic flux appears to be oriented in an unusual configuration, partially reversed relative to the main dipole field. This creates a local weakening at the surface. As the outer core dynamics shift, the anomaly shifts with them. Recent data from the European Space Agency's Swarm satellite constellation, which was launched specifically to map the magnetic field at high resolution and track its evolution over time, has revealed details about the anomaly that were not visible from ground-based measurements alone. The anomaly appears to be splitting, developing what some researchers describe as a secondary centre of minimum intensity over the South African region, while the original centre drifts westward. Whether this represents a temporary fluctuation in the outer core dynamics, or a structural change in how the field is organised beneath that region, is a question the magnetic research community is actively working to resolve. What makes the South Atlantic anomaly relevant to the rotation story is this. The same outer core dynamics that produce the magnetic field also produce the torque coupling between the outer core and the mantle. When the distribution of convective flow in the outer core shifts, both the magnetic field expression at the surface and the exchange of angular momentum between core and mantle shift simultaneously. They are different surface expressions of the same deep process. This means the magnetic field data and the rotation data are not two separate stories, they are different windows into the same phenomenon. Before exploring what that phenomenon might be, we need to address the inner core directly, because the inner core's behaviour has added a layer of complexity to this story that nobody fully anticipated. For decades, the working model of the inner core treated it as a passive participant in the planet's overall dynamics. It was solid, it was hot, it was slowly growing as the planet cooled and more iron crystallized out of the outer core liquid at the inner core boundary. Its rotation was thought to be closely locked to the mantle above it, turning with the planet more or less as a single unit. That picture changed in 1996 when researchers published seismic evidence suggesting the inner core was rotating slightly faster than the rest of the planet, a phenomenon called superrotation. Using seismic waves from repeating earthquakes that had occurred in similar locations decades apart, they found that the travel time for waves passing through the inner core had changed slightly between the two events. The only explanation consistent with the data was that the inner core had rotated relative to the mantle between the two measurements, changing the path the seismic waves travelled through the inner core's crystalline structure. The discovery generated substantial scientific debate. Different research groups using different earthquake pairs and different seismic stations produced different estimates of the superrotation rate, ranging from fractions of a degree per year to as much as 1 degree per year. The methodology was technically demanding and the uncertainties were large, but the general finding that the inner core could rotate at a different rate from the mantle was accepted broadly because it was physically consistent with models of core dynamics that predicted differential coupling between the liquid outer core and the solid inner core. Then, in late 2022 and into 2023, a new set of studies appeared that significantly complicated the picture. Researchers analysing a longer baseline of seismic data spanning several decades found evidence that the inner core's rotation relative to the mantle had not remained constant. It had slowed. In fact, by approximately 2009 to 2010, it appeared to have stopped its superrotation entirely relative to the mantle's frame and had begun to rotate in the opposite direction, slightly slower than the rest of the planet rather than slightly faster. The inner core was oscillating. This was unexpected, not impossible within the theoretical framework, but the timescale and the nature of the oscillation were not what the models had predicted. Some existing models had suggested oscillatory behavior in the inner core's rotation, driven by electromagnetic and gravitational coupling between the inner core, the outer core, and the mantle. But those models had predicted oscillation periods on the order of 30 years or more. The observed behavior appeared to be happening on a shorter timescale, with the transition from superrotation to subrotation occurring within roughly a decade. The implications extend in multiple directions. First, the inner core's differential rotation feeds back into the outer core's dynamics. If the inner core changes its rotation rate relative to the outer core liquid surrounding it, the coupling between them changes. The electromagnetic torque changes. The viscous shear at the inner core boundary changes. These changes in turn affect the convective patterns in the outer core, which affect both the magnetic field and the angular momentum exchange with the mantle above. Second, the inner core's rotation affects the seismic properties of the Earth as a whole. The inner core has a crystalline structure, with iron crystals preferentially aligned along certain axes due to the conditions under which they formed. How seismic waves travel through the inner core depends on the orientation of those crystal axes relative to the wave path. As the inner core rotates, the relationship between its crystal structure and the rest of the planet changes, subtly altering seismic travel times globally. These changes are small, but they are measurable with modern equipment and long baseline seismic records. Third, and most immediately relevant to everything else in this story, if the inner core began transitioning its rotation behavior around 2009 to 2010, that timing aligns with the beginning of the acceleration trend in Earth's surface rotation. The connection is not proven. The physical pathway from inner core rotation change to surface rotation acceleration involves multiple coupled systems and is not simple to model with confidence. But the timing alignment is not something researchers dismiss. It is one of the central questions driving current work in deep Earth geophysics. What would physically link them? The mechanism would run through angular momentum conservation in the coupled core mantle system. The total angular momentum of the Earth's interior must be conserved, ignoring external torques from the Moon, which operate on much longer timescales. If the inner core slows slightly in its rotation relative to the outer core, angular momentum must be redistributed. Some of that redistribution goes to the outer core. Some propagates upward through electromagnetic and viscous coupling to the mantle, and from the mantle to the crust. The surface, which is the crust, plus everything resting on it, absorbs the final expression of that redistribution as a change in rotation rate. The magnitude of such an effect from inner core rotation changes alone would be small, but small changes in the core can be amplified by resonance effects in the coupled system and by the other surface processes acting simultaneously. If the ice sheets are also redistributing mass in a way that would accelerate rotation, and if the atmospheric circulation is also shifting in ways that release braking torque on the crust, and if the core is simultaneously injecting angular momentum into the mantle, all three processes could reinforce each other in a way that produces the observed surface acceleration, even though no individual process would be sufficient to explain it alone. This is the coupled system problem that makes Earth science at its current frontier simultaneously exciting and humbling. The planet does not operate in clean, isolated compartments. The core talks to the mantle talks to the crust talks to the oceans and the atmosphere, the ice talks to the oceans, the atmosphere, and through gravitational redistribution to the rotation itself. Changes propagate across boundaries in all directions simultaneously, and the feedbacks run both ways. Understanding any one part of the system deeply requires modelling all the other parts at the same time, which pushes against the limits of both observational coverage and computational power. Let us stay near the surface for a moment and look at what the ice is actually doing, because the ice story is in some ways the most visually concrete piece of this puzzle, and it connects to the rotation through a mechanism that is elegant in its physics and alarming in its magnitude. When you think about ice sheets and sea level, you are probably thinking about the most direct effect. Ice melts, water flows into the ocean, sea level rises. That part is real and well documented. But the physical effect of ice mass redistribution on the planet's rotation is a different story, and it operates through the same principle that a figure skater uses when pulling their arms inward to spin faster. The physics is called the conservation of angular momentum. A rotating object's spin rate depends not just on how fast it is rotating, but on how its mass is distributed relative to its rotation axis. If mass moves closer to the rotation axis, the rotation speeds up. If mass moves farther away, the rotation slows. For Earth, the rotation axis runs roughly through the geographic poles. Mass distributed near the equator is far from the axis. Mass distributed near the poles is close to the axis. Ice sheets are not uniformly distributed across the planet. They are concentrated near the poles. Greenland's ice sheet sits between roughly 60 and 80 degrees north latitude. The Antarctic ice sheet covers the entire continent centered on the South Pole. When ice melts at these high latitudes and the water distributes itself across the global ocean, mass that was concentrated near the poles moves away from them, spreading across lower latitudes where it is farther from the rotation axis. This is like a spinning skater extending their arms outward, which should slow the rotation. And indeed, this is one of the traditional predictions of climate-driven ice melt, that it would contribute to a slight slowing of Earth's rotation over time. But here is where the modern data diverges from that simple prediction. The observed acceleration in Earth's rotation since approximately 2016 means something is counteracting or overpowering the slowing effect of ice redistribution. One candidate involves the specific geography of where ice loss is occurring most rapidly, and what happens to the Earth's shape as the ice load is removed. When a massive ice sheet rests on land, the enormous weight of billions of tons of ice depresses the crust beneath it. This is not a metaphor. The crust physically sinks under the load, and the mantle material beneath it flows outward to accommodate the depression. When the ice melts and the load is removed, the crust begins to rebound upward, a process called glacial isostatic adjustment. That rebound does not happen instantly. It happens over centuries and millennia because the mantle is highly viscous. But it does happen, and it redistributes mass in the vertical direction in a way that affects the planet's moment of inertia. The pattern of glacial isostatic adjustment currently underway in Greenland and parts of North America and Antarctica, as the crust rebounds from ice loads that melted at the end of the last ice age more than 10,000 years ago, is still actively ongoing. Greenland is rising. Parts of northern Canada and Scandinavia are rising. This vertical redistribution moves mass toward the poles, closer to the rotation axis, which contributes to rotational acceleration. The current pattern of rebound, combined with the ongoing modern ice loss, is not a simple net effect in one direction. It is a complex superposition of effects in opposite directions with different geographic distributions and different timescales, and the net outcome for rotation depends on which effect dominates in which decade. There is another dimension to this that involves not just the mass redistribution, but the gravitational fingerprint of the ice sheets themselves. Large ice sheets do not just sit passively on the planet. They pull ocean water toward them gravitationally. Greenland's ice mass is large enough that it attracts the surrounding ocean water, creating a regional sea level that is actually slightly higher near Greenland than it would be if the ice were absent. When Greenland loses ice, it loses gravitational pull on the surrounding ocean. The water that was attracted to Greenland migrates away, distributing itself across distant ocean basins. This creates a sea level fingerprint specific to Greenland melt, where sea level actually falls near Greenland and rises in the opposite hemisphere, particularly in the South Pacific and around the equatorial regions. This gravitational redistribution of ocean water has a rotational effect because it moves mass from polar latitudes to equatorial ones, which, as noted above, should contribute to slowing. But the rebound effect moves mass back toward the poles. The net is not zero and is not constant. It depends on the rate of melt versus the rate of rebound, which are changing on different timescales as the modern ice loss accelerates on top of the long-running adjustment from ancient deglaciation. What scientists are trying to untangle right now, using data from satellite gravity missions, primarily the GRACE and GRACEFO satellite pairs that measure Earth's gravitational field by tracking the distance between two satellites orbiting in formation, is the relative contribution of each of these effects to the observed changes in rotation and polar motion. The gravity measurements are sensitive enough to detect regional changes in ice mass at the level of centimeters of equivalent water height, which translates to the ability to track where mass is moving and at what rate across the whole planet. The data from GRACEFO over the past several years shows Greenland losing ice mass at an accelerating rate compared to the 20th century baseline. Antarctica is showing more complex patterns, with some regions losing mass rapidly and others showing relatively stable or even slightly increasing ice mass due to increased snowfall in some coastal sectors. The net for Antarctica is mass loss, but the geographic distribution of that loss matters for the rotation calculation in ways that uniform loss would not capture. Meanwhile, the observation that Earth has been spinning faster, despite the mass redistribution effect that should slow it down, tells us something important. The sum of all the other effects, core dynamics, atmospheric angular momentum exchange, ocean current changes, crustal rebound, must be contributing a net acceleration that outweighs the slowing from ice redistribution. Right now, in this decade, the balance could shift as the ice loss continues to accelerate in future years, potentially becoming large enough to reverse the observed acceleration trend even as other factors continue in the same direction. Or the other factors could intensify sufficiently to maintain or increase the acceleration. That uncertainty is real, and it is not a flaw in the science. It is what the data honestly shows. The atmosphere contributes to this story in ways that feel less dramatic than liquid iron cores and collapsing ice sheets, but are physically significant and continuously operating. The atmosphere is not a passive envelope resting on the planet. It is a massive fluid system, roughly 5 quadrillion kilograms of gas, rotating with the Earth and exchanging angular momentum with the crust through friction over mountains, coastlines, and ocean surfaces. When the atmospheric circulation speeds up relative to the crust, it absorbs angular momentum from the crust, and the crust slows slightly. When the atmospheric circulation slows, it returns angular momentum to the crust, and the crust speeds up. The jet streams are the most powerful, organized features of the atmospheric circulation, and their behavior has changed measurably over the past 2 decades. At high altitudes in both hemispheres, rivers of fast-moving air encircle the planet at mid-latitudes, separating cold polar air from warmer subtropical air. The strength and stability of the jet streams depends on the temperature gradient between the tropics and the poles. A larger gradient means a stronger, more stable jet stream. A reduced gradient means a weaker, more meandering one. As Arctic temperatures have risen at a rate roughly 3 to 4 times faster than the global average, a phenomenon researchers call Arctic amplification, the temperature gradient between the Arctic and the mid-latitudes has decreased. The jet streams have responded by weakening and developing larger amplitude meanders, waves of warm and cold air that extend further toward the poles and further toward the equator than they did in previous decades. This altered behavior changes where the atmospheric angular momentum exchange with the surface happens and at what magnitude. The net effect on Earth's rotation from these atmospheric circulation changes is not constant and is not easy to calculate in isolation, but it contributes to the overall angular momentum budget in ways that are measurable with modern atmospheric monitoring. The ocean is the 3rd great fluid system of the planet, and it too is changing in ways that connect to the rotation. The oceans cover roughly 71% of Earth's surface and contain more than 96% of the planet's liquid water. That mass is not stationary. It moves in organized patterns called ocean circulation systems, some driven by wind at the surface, others driven by density differences created by temperature and salinity gradients that extend through the full depth of the ocean. When ocean circulation patterns change, mass moves between ocean basins, angular momentum shifts, the planet's rotation responds. The most consequential ocean circulation system for this story is the one researchers call the Atlantic Meridional Overturning Circulation, sometimes abbreviated to AMOC, and sometimes referred to in popular science writing as the ocean conveyor belt. Though that analogy undersells its complexity significantly, the Atlantic Meridional Overturning Circulation is a vast system of interlocking ocean currents that moves warm surface water from the tropics northward into the North Atlantic and Arctic regions, where the water cools, becomes denser, sinks to depth, and flows back southward along the ocean floor. This circulation is driven by density differences, not by wind, which makes it fundamentally different from purely wind-driven surface currents, and also makes it sensitive to changes in temperature and salinity in specific critical regions. The Gulf Stream, which keeps Western Europe significantly warmer than it would otherwise be at comparable latitudes, is the most familiar surface component of this broader system. But the system extends from the surface to the ocean floor, from the tropics to the Arctic, and its strength at any given time depends on conditions in the North Atlantic where the sinking of dense water happens. If the water arriving in the North Atlantic is less dense than it needs to be to sink efficiently, the overturning weakens, and water becomes less dense when it is warmer or when it is diluted by freshwater input that reduces its salinity. Both of those things are happening in the North Atlantic right now. The ocean surface temperatures in the North Atlantic have risen with the overall warming trend, and the rapid melting of the Greenland ice sheet is adding enormous quantities of fresh water to the North Atlantic, precisely in the regions where the overturning circulation depends on dense, salty water sinking. The combination is acting like a brake on the AMOC. Proxy records that estimate the AMOC's strength over longer historical periods, derived from ocean sediment cores, the growth patterns of certain marine organisms, and ocean heat transport signatures, suggest that the current circulation strength may be near its weakest point in at least 1,000 years, possibly longer. Direct measurements of the AMOC using moored instrument arrays deployed across the Atlantic began only in 2004, so the instrumental record is short. But the data from those direct measurements, combined with the proxy estimates, paints a consistent picture of weakening that has accelerated during the same general period as the other anomalies described throughout this script. For the rotation, the AMOC matters because of how it redistributes the ocean's mass. A strong overturning circulation moves large volumes of water northward at the surface and southward at depth across thousands of kilometers of latitude. When that circulation weakens, the pattern of mass distribution across ocean basins changes. Water that would have been transported northward piles up at lower latitudes instead, and the deep return flow shifts. This redistribution has a measurable gravitational effect and a rotational signature that ocean circulation models can identify, though isolating it from all the other simultaneous changes is technically demanding. There is also a sea level dimension. When the AMOC weakens, the dynamic sea level along the eastern coast of North America rises because the circulation normally draws water away from that coastline. A weakened circulation leaves more water stacked against the coast. This is separate from the global sea level rise driven by ice melt and thermal expansion of warming water, and it adds a regional amplification to sea level changes that affects coastal infrastructure planning in ways that purely global projections miss. The interconnection does not stop there. Ocean circulation changes drive atmospheric circulation changes because the ocean and atmosphere exchange enormous quantities of heat, moisture, and momentum at the surface. When the North Atlantic becomes anomalously cool in certain regions due to the reduced heat transport from a weakening AMOC, the atmospheric temperature patterns over the North Atlantic and Western Europe respond. Those atmospheric anomalies influence the jet stream. The jet stream shifts influence weather patterns across the northern hemisphere, and those weather pattern shifts feed back into the ocean surface through changed wind stress patterns that affect the surface layer of ocean circulation. It is circular, deliberately, inexorably, mechanistically circular. Every change drives another change, which comes back to affect the original change in the next cycle through a different pathway. This is what scientists mean when they describe the Earth system as coupled. Not coupled in the way that two separate machines can be bolted together at a single interface. Coupled in the way that living systems are coupled through feedback loops at every level, operating simultaneously at different speeds, with effects that propagate far beyond where they originated. Understanding how all of this coupling affects the rotation requires stepping back from individual mechanisms and looking at what the combined measurements actually show across the full observation period. Since the early 1970s, scientists have maintained a global network of very long baseline interferometry stations, or VLBI stations, that measure Earth's rotation by timing the arrival of radio signals from extremely distant quasars. These extragalactic objects are so far away that they define a reference frame that is, for practical purposes, fixed in space. By comparing the precise timing of quasar signal arrivals at different stations around the planet, researchers can reconstruct the planet's exact rotation angle at any given moment to extraordinary precision. The technique has been continuously refined over decades and now constitutes the primary basis for Earth orientation measurements that feed into the international timekeeping infrastructure. The VLBI data, combined with satellite laser ranging measurements and global navigation satellite system data that provide complementary constraints, gives scientists a continuous record of Earth's rotation rate going back roughly 50 years with high precision, and a lower precision record extending further back through historical astronomical observations. That record shows the following with clarity that the scientific community considers unambiguous. From approximately 1972 to roughly 2016, Earth's rotation showed the expected pattern of gradual slowing, punctuated by irregular short-term fluctuations from atmospheric and ocean angular momentum changes. The general trend over that period was consistent with tidal braking by the Moon, modified by the annual cycle of atmospheric angular momentum changes and the irregular multi-year fluctuations driven by El Niño and La Niña events in the Pacific, which shift large masses of warm water between western and eastern Pacific basins and create detectable rotation signals. Beginning around 2016, the trend changed. Days started coming in shorter than the 50-year average, with increasing regularity. The frequency of record short days increased. And by 2020, 2021, and 2022, the planet was recording days that were not just shorter than the recent average, but shorter than anything measured in the modern precision record. The deviation from the long-term baseline was not catastrophic in absolute terms, but its statistical significance within the context of the full record is high, and its persistence across multiple years rules out simple attribution to a single El Niño event or a single atmospheric fluctuation. What the record also shows is that Earth's polar motion, the wandering of the geographic poles relative to the crust, has been changing. The geographic poles are not fixed points. They drift slowly over the surface due to shifts in the distribution of mass inside and on the planet. The direction and rate of that drift has been measured continuously since the late 19th century, and for most of the 20th century, the pole moved in a relatively consistent direction. Around the year 2000, the direction changed noticeably. The North Pole began drifting eastward at a faster rate than before. Analysis of the timing and magnitude of the polar drift change using GRACE satellite gravity data has attributed a significant portion of it to ice mass loss in Greenland and the redistribution of water mass across the globe. The melting of Greenland's ice is shifting where the planet's mass is concentrated at high latitudes, and the poles respond by migrating toward the new center of mass distribution. Antarctica's complex pattern of regional ice gain and loss also contributes, and glacial isostatic adjustment from ancient ice age deglaciation adds a background signal that has been operating for thousands of years and will continue for thousands more. Polar motion matters for more than navigation corrections, though those corrections are required for every GPS and satellite positioning calculation to maintain accuracy. Polar motion is another independent measurement of mass redistribution on and within the planet, and its acceleration since approximately 2000 reinforces the story told by the rotation rate data, the gravity measurements, and the magnetic field observations. Multiple independent instruments, multiple independent teams, multiple independent physical phenomena are all pointing in the same direction. Something changed in the Earth system around the turn of this century, and the changes have been intensifying through the 2 decades since. The magnetic field story, which was introduced briefly in the context of the South Atlantic anomaly and the outer core, deserves a fuller treatment because its implications extend beyond the rotation question into some of the most consequential geophysical risks on the geological timescale. The magnetic field is generated by the outer core's motion, but its effects reach far above the surface into space. Earth's magnetosphere, the region of space where the magnetic field is strong enough to deflect charged particles from the Sun, extends tens of thousands of kilometers outward on the sunward side and much farther in the tail that stretches away from the sun on the night side. The magnetosphere is the planet's primary shield against the solar wind and against high-energy cosmic rays from more distant sources. The solar wind is not gentle. It is a continuous stream of charged particles moving at hundreds of kilometers per second, carrying the sun's magnetic field embedded within it. When it reaches Earth, the magnetosphere deflects most of it around the planet, channeling only a fraction into the polar regions where it creates the auroras. Without the magnetosphere, the solar wind would gradually strip the upper atmosphere, exposing the surface to ultraviolet radiation and ionizing radiation at levels currently mitigated by the atmosphere. The geological evidence from the Martian surface, which lost most of its magnetosphere billions of years ago and subsequently lost most of its atmosphere, illustrates what a magnetosphere does over geological time for a planet that has one, and what happens to one that does not. Periodic geomagnetic reversals, events in which the north and south magnetic poles switch places, are recorded in the geological record going back hundreds of millions of years. The evidence is preserved in oceanic crust created at mid-ocean ridges where molten rock emerging from beneath the crust cools and solidifies, locking in the orientation of the magnetic field at the time of solidification. The resulting magnetic stripes on either side of mid-ocean ridges constitute a tape recording of geomagnetic reversals going back through geological time. The reversals happen irregularly, with intervals ranging from tens of thousands to millions of years between events. The most recent full reversal, called the Brunnes-Matuyama reversal, occurred approximately 780,000 years ago. Before that, there was a shorter reversal event called the Laschamp excursion approximately 41,000 years ago, which was brief enough by geological standards that the magnetic poles did not fully exchange, but did wander dramatically, and the field weakened significantly before recovering. More recently, on the geological timescale, an event called the Gothenburg excursion occurred roughly 12,000 to 13,000 years ago, though this is less well established in the record. A full geomagnetic reversal typically takes between 1,000 and 10,000 years to complete. During a reversal, the overall field strength decreases significantly, often to a fraction of its present value. The magnetic poles do not simply flip. They break up into multiple local poles that wander across different latitudes before recoalescing in the reversed configuration. During this breakdown phase, the protection the magnetosphere provides against the solar wind and cosmic rays is substantially reduced over large areas of the planet. The consequences for the modern world of living through a significant portion of a geomagnetic reversal or excursion would be substantial. Satellite electronics are vulnerable to high-energy charged particles. Power grid transformers, particularly the large high-voltage transformers that are the most difficult to replace and the most central to grid stability, are vulnerable to geomagnetically induced currents during intense magnetic disturbances. Navigation systems that depend on magnetic field orientation would require continuous recalibration. The increased radiation reaching the surface at lower latitudes than the current polar regions would have biological effects that are debated in magnitude, but not in direction. Critically, none of these are hypothetical concerns invented for the purpose of generating alarm. They are engineering realities that the satellite industry already manages around solar activity cycles, and that power grid operators in regions prone to geomagnetic storms already factor into their risk planning. A prolonged reversal transition would represent a sustained version of the elevated risk that currently exists only during transient geomagnetic storm events triggered by solar coronal mass ejections. The question of whether Earth is currently approaching a reversal or excursion is one that the geomagnetic research community approaches with appropriate caution. The field's weakening over the past century and a half is real and well documented. The South Atlantic anomalies expansion and apparent splitting is real. The accelerated drift of the magnetic North Pole since the 1990s is real. What is not established is whether these observations represent the beginning of a transition to a reversal, a temporary excursion that will recover without completing a full reversal, or simply an unusually deep fluctuation within the normal variability of the geodynamo. The honest position, stated by researchers who specialize in paleomagnetism and geodynamo modeling, is that the current observations are consistent with multiple scenarios. They are consistent with the early stages of a reversal. They are also consistent with recovery without reversal. The geological record shows that the field has been at roughly its current strength and declining at roughly its current rate before, and has recovered without reversing. It also shows transitions that look similar in early stages and did proceed to full reversal. Distinguishing between these paths before the outcome is resolved requires either a much longer observational record than we currently have, or a physical model of the geodynamo that can reliably predict future behavior from present state, and neither of those tools is fully available yet. What is available is better monitoring than at any previous point in history. The Swarm satellite constellation is producing the highest resolution continuous maps of the magnetic field ever made. Ground-based observatories are adding data at high temporal resolution, and computational models of the geodynamo have improved substantially over the past decade as processing power has increased. The monitoring infrastructure now exists to detect changes at early enough stages to give meaningful warning time for the systems most vulnerable to field changes. That is not nothing. In fact, for a geophysical process that operates on timescales of thousands of years, having a robust monitoring system running decades in advance is genuinely significant. The connection between the magnetic field's current behavior and the rotation acceleration runs through the outer core dynamics as described earlier. But there is a second, less direct connection that operates through the ionosphere, the charged upper atmosphere layer, where Earth's atmospheric physics overlaps with the magnetosphere. The ionosphere is shaped by the magnetic field, and its behavior affects the propagation of radio signals used by GPS and communication satellites. As the magnetic field shifts, the ionospheric structure shifts with it, changing where signals are refracted and absorbed. This creates a long-term drift in the calibration corrections required for satellite navigation systems, independent of the rotation-driven timing corrections discussed earlier. Both corrections are manageable with proper monitoring, but both require continuous attention and ongoing adjustment, and both become more demanding as the field changes faster. There is a layer of this entire story that requires direct acknowledgement, the human dimension, not in the sense of human responsibility for these planetary changes, most of which are driven by processes far deeper and far more ancient than any human activity, but in the sense of what human civilization has built during the unusually stable geophysical period of the past 10,000 years, and what it means for those constructions now that the stability is shifting. Human civilization is approximately 10,000 years old if you measure from the earliest agricultural settlements and the first persistent organized communities. Every significant development in that arc, from the first cities to the Industrial Revolution to the modern satellite-networked global economy, happened during a geophysical window that was, by the standards of Earth's full history, unusually calm. The magnetic field was relatively stable by geological norms. The ice sheets were in a post-glacial configuration that had settled into a rough equilibrium. Sea levels had risen from their glacial low point and then stabilized. The rotation rate varied within a narrow band. The monsoon systems and ocean circulation patterns that agriculture across Asia, Africa, and the Americas depends on were operating in configurations that could be mapped and predicted with reasonable reliability across generations. Human societies built their infrastructure on those conditions. Coastal cities were founded at elevations that assumed sea level would not change rapidly within the time frame of a civilization. Agricultural systems were developed in regions where precipitation patterns had been broadly consistent for generations. Trade routes across the oceans were established based on predictable wind and current patterns. The global infrastructure of the modern era, the satellite networks, the power grids, the financial systems, the shipping lanes, the aquifer systems, was engineered with explicit and implicit assumptions about the physical environment it would operate in. Some of those assumptions are now being tested by changes that are operating faster than the 10,000-year geological baseline would suggest. Not all of them are being tested equally. Some of the changes are slow enough and the infrastructure robust enough that the adjustment is manageable within existing engineering and institutional capabilities. Others are approaching thresholds where the rate of change is outpacing the institutional capacity to adapt, and the distinction between those two categories is not always obvious until a threshold has already been crossed. Sea level rise from ice melt is the most familiar example. The engineering solutions for protecting coastal infrastructure exist. Seawalls, managed retreat from low-lying areas, elevation of critical facilities. These are understood and in some cases already underway, but they are expensive. They require decades of lead time to implement at scale, and the political and economic complexity of coordinating them across hundreds of independent national and local jurisdictions creates friction that slows implementation even when the technical path is clear. The rate at which sea level rise accelerates determines whether that friction can be overcome in time, and the rate of acceleration is not fully predictable because it depends in part on ice sheet dynamics that are still not perfectly modelled, particularly the behaviour of marine ice sheets in West Antarctica, where the potential for rapid dynamical collapse rather than gradual surface melt introduces scenarios that could significantly exceed the near-term projections. The rotation and timekeeping problem, while technically arcane, illustrates a different dimension of the same fundamental challenge. The entire global infrastructure of synchronized time, from GPS satellites to financial exchange timestamps to power grid coordination, was built on the assumption that Earth's rotation was predictable within the bounds captured by the existing leap-second system. The planet has now moved outside those assumptions in a direction the system was not designed to handle, specifically the need for a negative leap second or an alternative mechanism. The engineering community is aware of the problem. Working groups have been actively discussing solutions for years. A decision has not been fully locked in globally because the solution involves coordinating changes across telecommunications, standards, bodies, satellite operations centers, financial regulatory frameworks, and power grid management systems across dozens of countries simultaneously, all of which have different update cycles, different governance structures, and different risk tolerances. This is not a failure of engineering competence. It is an illustration of how the organizational complexity of modern civilization creates inertia that slows response to physical changes even when the physical changes are well understood. The planet does not wait for organizational consensus. It continues rotating at whatever rate the physics of its coupled systems dictates, accumulating the divergence between physical reality and the infrastructure calibrated to an older physical reality. The same dynamic operates across the other changes described in this script. The magnetic field drift requires continuous recalibration of navigation systems. The systems exist to do that recalibration, but the recalibration has to be done proactively, ahead of the drift, not reactively after GPS errors begin appearing in critical applications. The infrastructure for doing it proactively exists, but requires ongoing funding, coordination, and institutional attention in an environment where institutional attention is always in competition with more immediate demands. The ocean circulation changes require updates to climate projections that feed into coastal planning, agricultural policy, and water resource management across entire continents. The science is improving. The projections are being updated, but the pipeline from improved scientific understanding to changed engineering standards to revised infrastructure plans to actual built infrastructure runs through a multi-decade implementation cycle, even in the most responsive, institutional environments. The faster the underlying conditions change, the shorter the lead time available before the gap between built infrastructure and actual physical conditions becomes an operational problem rather than a planning concern. This is not pessimism about human institutional capacity. Civilizations have adapted to major geophysical changes before, including the end of the last ice age, the Holocene climate transition, and multiple shorter-term climate fluctuations over historical timescales. The difference now is the degree of infrastructure interdependence that creates cascading risks when any individual system is stressed. In a pre-industrial world, a disruption to one region's agricultural production was catastrophic for that region, but did not immediately affect food security in distant continents. In the modern, globally integrated supply chain, a disruption to critical agricultural regions, key ports, or major power grid nodes propagates through the interconnected system far faster and across far greater distances than any previous era of human organization. The risk is not that any individual geophysical change will overwhelm civilization on its own. The risk is that multiple simultaneous pressures on interdependent systems create failures that compound across those connections in ways that exceed the design margins built into any individual component of the infrastructure. The modern global economy, the energy grid, the food supply chain, the freshwater management systems, and the communication and navigation infrastructure all share a common characteristic. They were designed with redundancy and safety margins calibrated to the variability of the past, not the variability of a planet in transition. Recalibrating those margins for the current trajectory is the engineering and governance challenge of the coming generation, and it begins with understanding clearly what the planet is actually doing. To appreciate the full scope of what is happening, it helps to think about timescales explicitly, because one of the most common sources of confusion in discussions of planetary change is the conflation of processes that operate on very different temporal scales. Some of the changes described in this script are operating on timescales of years to decades. Some operate on timescales of centuries to millennia. Some operate on timescales of tens of thousands to millions of years. They are all happening simultaneously, and they interact across timescales in ways that produce effects on every level. The leap second problem is a years to decades timescale issue. The solution needs to be implemented within the current decade, or the divergence between atomic time and Earth time becomes unmanageable without a large disruptive correction. The ocean circulation weakening is a decades to centuries timescale issue. A significant weakening of the AMOC would play out over generations, affecting precipitation patterns, storm tracks, and regional sea level along both sides of the North Atlantic over centuries. The glacial isostatic adjustment from the last ice age is a millennia timescale process. The crust will continue rebounding in formerly glaciated regions for thousands of years, regardless of what modern ice loss does or does not add to the load history. The geomagnetic reversal, if one is underway, is a timescale of hundreds to thousands of years for the transition process. These processes do not cancel each other out because they operate on different timescales. They superimpose. The fast processes create pressures on infrastructure in the near term. The medium timescale processes create constraints on planning that extend beyond any current political cycle. The long timescale processes define the backdrop against which all the shorter-term changes are happening, and they create conditions that will constrain the planet's geophysical behavior for generations far beyond any current institutional planning horizon. The honest reckoning with this picture requires acknowledging both what we know well and what remains genuinely uncertain. The measurements of rotation rate, polar motion, ice mass loss, magnetic field strength, and ocean circulation are all well established by multiple independent methods. The physical mechanisms connecting these measurements to the processes described throughout this script are all grounded in well-tested geophysical theory. The observation that multiple systems appear to be departing from their historical baselines within roughly the same temporal window is not a constructed narrative. It is what the data shows when you align independent time series from independent sources on a common timeline. What remains genuinely uncertain is the future trajectory. Science is not in the business of false certainty, and any representation of these changes that claims to know precisely where the planet is heading on any of these dimensions is misrepresenting what the actual state of knowledge is. Models can project scenarios. Scenarios can be assigned relative likelihoods based on what is known about the driving mechanisms. But the coupled nature of the Earth system means that surprises are not just possible, they are historically normal. The geological record is full of transitions that happened faster, slower, or in different directions than the preceding trend suggested. The planet has non-linear behavior at its core, literally and figuratively, and non-linear systems can produce rapid shifts that look discontinuous from the outside, even though they are the result of gradual accumulation of stress on underlying structure. What this means practically is not that we should act as if worst-case scenarios are certain. It means we should build and maintain the monitoring systems that give the earliest possible warning of changes exceeding projected bounds. It means we should invest in the redundancy and adaptability of critical infrastructure rather than optimizing purely for efficiency under current conditions. It means we should support the scientific research that improves our understanding of the mechanisms well enough to shrink the uncertainty in the projections. And it means we should engage with the complexity honestly rather than collapsing it into either false alarm or false reassurance. The planet is 4.5 billion years old. It has been through conditions far more extreme than anything currently measured or projected within the next few centuries. It will continue to exist long after any current human concern has resolved itself one way or another. The geophysical changes described throughout this script are not a crisis for the planet, they are a challenge for the civilization that happens to be living on the planet during this particular window of its history. That window, the period of post-glacial geological stability that allowed 10,000 years of agricultural civilization and all the complexity built on top of it, was always a temporary feature of a dynamic planet. What is happening now is the transition out of that window. Whether the transition takes decades, centuries, or millennia to work through, and whether the new conditions on the other side are broadly hospitable to the civilization that currently exists, depends on a combination of planetary physics and human choices that are both still unresolved. The physics is not waiting for us to decide how to think about it. The rotation is what it is. The core is doing what it is doing. The ice is melting at the rate it is melting. The magnetic field is shifting at the pace the outer core dynamics dictate. These are not things that respond to human opinion or institutional preference. They are measurements taken by instruments, reviewed by scientists, published in journals, and replicated across independent research programs on multiple continents. The data is what it is. What humans control is the response, the investment in monitoring, the engineering of adaptive infrastructure, the governance of shared global systems, and the quality of public understanding about what is actually happening to the planet that every living person shares. That last item, the quality of public understanding, is where the gap between what the science shows and what most people know is currently widest. And a wide gap between reality and public understanding in a democracy is itself a risk to the quality of the institutional response. This is not a call for alarm, it is a call for clarity. The facts described in this script are not secret. They are not contested within the scientific community. They are published, replicated, and freely available to anyone who looks for them in the primary literature. What they require is translation from technical language into terms that make the connections visible to anyone who has not spent years inside the relevant field, because the connections are what matter. Any one of these phenomena, faster rotation, inner core oscillation, weakening magnetic field, accelerating ice loss, slowing ocean circulation, shifting jet streams, wandering poles, could be discussed in isolation as an interesting but bounded scientific observation. Together, converging on the same temporal window, they are something more, a signal of planetary scale reorganization that has implications for every system humans have built to depend on planetary stability. The scientific community is not unified on exactly how much of this convergence is explained by a single shared driver versus the superposition of multiple independent processes that happen to be operating on similar timescales for different reasons. That debate is ongoing and productive. The data is driving it forward faster than any individual researcher or institution could alone. And the emerging consensus, while not finalized on every detail, is pointing increasingly clearly toward a coupled interpretation. The systems are not changing independently. They are changing together because they are coupled together, and a change in one propagates into the others through pathways that span from the center of the planet to the edge of the atmosphere. The next step in understanding this story fully is to look at what the data shows when all the independent time series are placed on a single timeline and examined as a system rather than as separate phenomena. That synthesis is where the picture becomes clearest, and also where the most important unanswered questions emerge in sharpest relief. When researchers who specialize in Earth's geophysical behavior compare notes across the boundaries of their individual sub-disciplines, something consistently strikes them as significant. Not the individual anomalies, which they deal with every day in the context of their specific instruments and datasets, but the timing. The timing of when each individual system began to deviate from its historical baseline shows a pattern that is not random. Rotation rate data shows the acceleration emerging clearly from background noise around 2016, with antecedent signs visible in the data as far back as 2012 to 2013, depending on the smoothing applied. Inner core rotation data, extrapolated backward from the seismic record, suggests the transition from superrotation to the current behavior began in the window of roughly 2009 to 2012. Outer core angular momentum, estimates derived from the rate of change in the surface magnetic field, show a shift in the same general window. Greenland ice mass loss rate data shows a step change acceleration beginning around 2012 and steepening through the mid-2010s. The South Atlantic anomaly's minimum field intensity, tracked since satellite measurements became available in the 1970s, shows a consistent long-term decline, but with a steeper gradient emerging in the mid-2010s. Arctic sea ice extent, used as a proxy for the atmospheric circulation changes affecting jet stream behavior, shows its sharpest multi-year decline beginning around 2012. Atlantic meridional overturning circulation strength estimates, derived from a combination of direct measurements and proxy records, show accelerating weakening concentrated in the mid-2010s. Polar motion direction change, as measured by the IERS, the International Earth Rotation and Reference System Service, shows a clear deviation from the 20th century trend beginning around the year 2000, with acceleration of the new trend through the following decade. Each of these time series was measured independently, Each was processed by different researchers at different institutions, using different instruments and different methodologies. Each was published in peer-reviewed journals where the data, methods, and interpretations were scrutinized by other specialists. And each one, when placed on the same timeline and normalized to a common scale, shows its most notable departure from its respective historical baseline within the same broad decadal window, centered on approximately 2009 to 2016. The probability that 7 or 8 independent geophysical systems would all depart from their historical baselines within the same decade by random coincidence, with no shared physical driver, is not zero. Unlikely events happen. But the probability is small enough that researchers who study these systems find the coincidence difficult to dismiss as noise. The more natural interpretation, and the one that is driving increasing cross-disciplinary collaboration, is that these systems share a common excitation or a common set of mutually reinforcing changes that propagated across coupled layers of the Earth system during that window. What that common excitation might be is the hardest question in current geophysical research, and it does not yet have a single agreed answer. Several candidate frameworks exist, and they are not mutually exclusive. One framework centers on the inner core. If the inner core's oscillatory behavior brought it to a transition point around 2009 to 2012, the resulting change in angular momentum coupling between the inner core, outer core, and mantle could have sent a signal upward through the coupled system that manifested in surface rotation changes, outer core circulation shifts, and magnetic field anomalies simultaneously. The timescale of such propagation through the mantle is poorly constrained but plausibly consistent with the observed sequence of changes appearing at different depths on slightly different timescales. A second framework emphasizes the role of the climate system as the primary driver. Rapid Arctic warming, accelerating Greenland ice loss, weakening AMOC, and jet stream changes are all connected to each other through well-understood atmospheric and oceanic mechanisms. If this climate system reorganization began in earnest around 2009 to 2012, it could explain many of the surface level changes, while the core changes are either independent or a secondary response to long period mantle dynamics that happen to be occurring on a similar timescale by coincidence. A third framework attempts to integrate both of the above, treating the climate system changes and the deep Earth changes as parallel responses to a longer period oscillation in the coupled Earth system that is not yet fully characterized. Some researchers point to multi-decadal oscillations in ocean circulation, the Atlantic multi-decadal oscillation and the Pacific decadal oscillation, as organizational features of the climate system that can synchronize surface changes across ocean basins. Others point to longer period oscillations in core dynamics that have been proposed theoretically but are difficult to verify observationally given the short time span of precise measurements. None of these frameworks is definitively ruled in or ruled out by current data. The data is insufficient to distinguish between them with confidence. What more data will do, and what the ongoing monitoring programs across all these systems are designed to produce, is narrow the range of possibilities by constraining the parameters in the competing models. Each additional year of high-precision measurement, from GRACEFO, from the Swarm constellation, from the VLBI network, from the AMOC mooring arrays, and from seismic networks monitoring the deep Earth, adds resolution to a picture that is still coming into focus. What the picture already shows clearly enough to act on is the coupled nature of the changes and the direction of their combined effect on the infrastructure and systems that modern civilization depends on. The planet is reorganizing at multiple levels simultaneously. The reorganization is measurable, it is continuing, and the systems humans have built are operating increasingly close to the edges of the design assumptions that were calibrated to a more stable Earth. That is not a reason for despair. It is a reason for clarity, for investment in understanding, and for the kind of honest reckoning with physical reality that has always been the foundation of effective human response to a changing world. The Earth has been changing for 4.5 billion years. Every organism that has ever lived on it has done so on a planet in motion, a planet that shifts and breathes and reorganizes across timescales from seconds to eons. What is different now is not that the planet is changing. What is different is the degree to which human civilization has built its foundations on the assumption that the rate of change would remain within the narrow bounds of the geological stability window that is now, by multiple independent measures, ending. There is a question that sits underneath all the data, underneath all the measurements and the model outputs and the conference proceedings and the peer-reviewed publications. It is not a technical question. It is not answered by better instrumentation or faster computers or more refined satellite constellations. It is a question about what it means to live on a planet that is actively changing in ways that exceed the assumptions civilization was built on, and to know that it is happening in real time. Most of human history was shaped by planetary forces that people could observe but not measure with precision. Floods came, droughts came, volcanic eruptions reshaped landscapes, earthquakes destroyed cities, diseases swept through populations. But the deeper, slower changes, the ones operating over centuries and millennia and geological epochs, were invisible to human observers not because they were not happening, but because no human lifespan was long enough to see them clearly. The changes that are now being measured were always occurring. What is new is the capacity to see them. That capacity is genuinely remarkable and genuinely recent. The precise measurement of Earth's rotation to millisecond accuracy has been possible for less than a century. The satellite monitoring of ice sheet mass from orbit began in the early 2000s. The direct measurement of deep ocean circulation using moored instruments began in 2004. The high-resolution continuous mapping of the magnetic field from dedicated satellite constellations began with the Swarm launch in 2013. Seismic networks dense enough to resolve the inner core's rotation behavior accumulated their essential database over the past 4 decades. In each case, the instrument that revealed the anomaly was built within living memory. Some were built within the past decade. This creates a peculiar situation for understanding what is actually new versus what has always been happening and is only now visible. When the GRACE satellites showed Greenland losing ice mass at an accelerating rate, that acceleration was real. But was the acceleration unprecedented? Or was ice loss at similar rates happening in previous decades and centuries, simply undetected because the instruments did not exist to measure it? For some of the changes described throughout this script, the answer is knowable through proxy records. Ice cores drilled from the Greenland and Antarctic ice sheets preserve a record of past accumulation and temperature going back hundreds of thousands of years, and the rates of change currently observed in some metrics do appear to be outside the range of natural variability captured in those records. For others, particularly the deep Earth processes, the proxy record is sparse and the comparison is genuinely difficult. What researchers are careful to say, and what the evidence actually supports, is not that every individual change is without precedent in Earth's full history. Many of these changes have happened before, some in greater magnitude, during different geological periods under different boundary conditions. What they say is that the simultaneous convergence of multiple systems showing departure from their recent baselines within the same decade, on top of boundary conditions created by a climate system warming faster than at any point in at least the past several 100,000 years, is a combination that has not been directly observed before in the record accessible to current science. That last qualification matters. The record accessible to current science. Science can reconstruct the past only as far back and at only the resolution that preserved physical evidence allows. The absence of a documented precedent for what is currently observed does not prove that no precedent exists. It proves that if a precedent exists, either it was not preserved in a form detectable by current methods, or it is beyond the temporal reach of those methods, or it has simply not yet been found. Honest science acknowledges this. It does not use the absence of a precisely comparable historical precedent as proof of catastrophe any more than it uses the same absence as proof of safety. What it does use is the measurements themselves, their rates of change, their directions, their convergences, and the physical mechanisms understood well enough to project them forward with quantified uncertainty. And on that basis, the current trajectory on multiple dimensions simultaneously points toward conditions that will strain the infrastructure of modern civilization increasingly over the coming decades. Regardless of which specific mechanism turns out to be the dominant driver, the people whose work sits closest to this dataset are not, on the whole, the loudest voices in the public conversation about Earth's future. Geophysicists who study core dynamics tend not to appear on news programs. Specialists in geodesy and Earth rotation do not typically write best-selling books for general audiences. The researchers running the VLBI networks and maintaining the seismic arrays and analysing the swarm data are working in environments defined by academic publication cycles, grant funding structures, and the norms of highly technical disciplines that prize precision over accessibility. The result is a significant gap between what the technical community understands about the state of the planet's deep geophysical behaviour and what the general public knows about it. That gap is not primarily the public's failure. It is a consequence of the structure of how specialised scientific knowledge is produced and communicated. The technical language of geophysics, the notation systems, the reliance on prior knowledge of concepts like angular momentum coupling and geomagnetic field tensor components and seismic anisotropy creates barriers to understanding that are real, even for highly educated non-specialists. And when the general science communication ecosystem does cover topics like Earth's rotation or the magnetic field, the coverage tends toward either sensationalism or reassurance, both of which flatten the genuinely complex and uncertain picture into something simpler than the data actually shows. The sensationalist version tells you that the poles are about to flip and civilization will collapse. The reassurance version tells you that everything is fine, the changes are tiny and inconsequential, scientists have it under control. Both versions are wrong. The actual picture is harder to hold in mind, but far more interesting and far more relevant to the decisions being made about infrastructure, policy, and resource allocation right now. The changes are real, and they are significant. The consequences are serious and require attention. The uncertainty is also real and should not be papered over with false confidence in either direction. Living with genuine uncertainty about consequential geophysical change is uncomfortable. Human cognition tends to prefer certainty, even false certainty, over an honest acknowledgement of an open question. This is well documented in the psychology of risk perception. People find it easier to decide that something is either fine or catastrophic than to hold in mind a probability distribution of outcomes ranging from manageable to severe, with the position on that distribution depending on factors that are not yet fully resolved. The scientific community's honest position that the planet is changing faster than the recent baseline in multiple coupled systems simultaneously, and that the outcome depends on how tightly coupled feedbacks amplify or dampen those changes over the coming decades, does not map cleanly onto either of the cognitive shortcuts most people reach for. What maps better onto the actual situation is an engineering mindset rather than a predictive one. An engineer designing a bridge does not need to know exactly when and in what form stresses will arrive. They need to know the range of plausible stresses and build sufficient margin to handle the upper end of that range. When the range of plausible stresses shifts upward because the environment the bridge operates in has changed, the engineering response is not to demand certainty about the new stress level before doing anything. It is to assess the current margin, identify where it falls short, and prioritize the upgrades that address the largest gaps first. That is the appropriate frame for responding to what is being measured in Earth's geophysical systems right now. Not certainty about catastrophe, not dismissal of the changes as inconsequential, but an honest assessment of where the margins in critical systems are thinnest relative to the direction and rate of change in the underlying physical conditions, followed by prioritization of the investments and institutional changes that would expand those margins most effectively. The satellite timekeeping infrastructure is an example where the margin is already thin and the path to expanding it is clear, if organizationally complex. The solution exists. It has been designed. It requires international coordination to implement across the relevant standards, bodies, and operational systems. The barrier is not technical knowledge, but institutional momentum. Prioritizing the resolution of the negative leap-second question before the divergence forces an emergency correction is straightforwardly achievable with existing tools and existing institutions. If those institutions treat it as the Profit 7 priority it deserves to be. The power grid infrastructure in regions most vulnerable to geomagnetically induced currents is another example. The specific types of high-voltage transformers most vulnerable to damage from geomagnetic storm events, the large extra high voltage units that take 18 months to 2 years to manufacture and cannot be easily stockpiled as spares, are known. The regions where grid topology makes cascading failures most likely during a major geomagnetic event are mapped. The protective measures that would reduce the risk, including automatic disconnection protocols, additional shielding on vulnerable transformers, and diversified routing that avoids the most dangerous configurations, are understood in principle. What they require is capital investment and regulatory commitment to standards that reflect the risk of a stronger magnetic disturbance than has been recorded during the short history of the modern grid. The most recent comparable event, the 1989 geomagnetic storm that caused a 9-hour power outage across the Canadian province of Quebec, damaged transformers across the northeastern United States, and disrupted satellite operations, occurred before the current level of grid interconnection and before the expansion of extra high voltage transmission infrastructure. A similar event today would encounter a more extensive and more interconnected grid than 1989, but also a grid with more high value and difficult to replace components than existed then. The net risk, accounting for both the greater exposure and the improved monitoring and some improved protective measures, is considered by grid reliability organizations to be higher than it was in 1989, not lower. And the current trajectory of the magnetic field, with its ongoing weakening, particularly in the South Atlantic anomaly region, suggests that the shielding the magnetosphere provides against energetic solar events is on a downward trend, not an upward one. Coastal infrastructure planning is the example where the timescale mismatch between the physical change and the institutional planning cycle is most acute. Major coastal infrastructure, port facilities, flood protection systems, wastewater treatment plants, transportation corridors, and urban development is built with design lifespans of 50 to 100 years. Decisions being made now about where to build, what elevation to build at, and what flood protection to incorporate will still be producing consequences in the 2080s and beyond. The physical changes in ice loss and ocean circulation are already committed to trajectories that will produce meaningfully different sea level and storm surge conditions by the 2050s compared to the baseline assumptions in most FRIND current planning codes. The disconnect between the planning timescales and the physical timescales creates what researchers in infrastructure resilience call a commitment gap. Infrastructure built today under current planning assumptions will be operating in physical conditions that exceed those assumptions before the end of its design life. The commitment gap is not inevitable. It can be closed by updating the planning assumptions to reflect the actual projected physical conditions over the relevant design lifespan. But updating planning assumptions requires political will, clear communication of what the projections actually show, and the institutional capacity to translate improved projections into changed standards and regulations before the infrastructure that will be affected is already built. The agricultural system faces a version of this challenge on a global scale. The crops that feed the majority of the world's population were developed and optimized for the climatic conditions of the 20th century. Their cultivars, their planting calendars, their irrigation demands, their pest and disease resistance profiles are calibrated to temperature ranges, precipitation patterns, and growing season lengths that are now shifting in every agricultural region on Earth at a rate faster than historical variability. The adaptation tools exist: plant breeding, agronomic practice changes, irrigation system modification, crop diversification, but implementing them at the scale required to maintain global food production, while the physical environment shifts, requires both technical investment and institutional coordination across national food systems that are, in many cases, not designed for coordinated response to global geophysical change. The freshwater system is perhaps the least visible of the critical infrastructure dimensions affected by the changes described throughout this script, but it is in some respects the most immediate in its consequences for human welfare. A significant fraction of the world's population depends on glacially fed river systems for freshwater supply. Mountain glaciers that have been building over thousands of years are retreating in virtually every mountain range on Earth at rates that are accelerating. In the short term, glacial retreat produces increased meltwater flow, temporarily augmenting river discharge. In the medium and long term, as glaciers shrink below critical mass, the meltwater contribution collapses, and rivers that entire regions depend on shrink dramatically in low precipitation seasons when glacial melt was previously the primary source. The timing of this transition varies by glacier size, elevation, and local climate trajectory, but the direction is unambiguous across essentially every monitored mountain glacier system on the planet. The Himalayan glaciers that feed the great rivers of South and East Asia, the Andes glaciers that feed rivers in South America, the Alpine glaciers that contribute to European river systems, all are losing mass. The communities and agricultural systems and urban water supplies that depend on those rivers are in varying stages of recognizing and responding to the long-term trajectory. The responses exist: reservoir expansion, groundwater management, demand reduction, water recycling, crop shifts to less water-intensive varieties. But they require lead time and investment, and lead time is the resource that the rate of glacial retreat is consuming fastest. None of this is speculation. None of it requires assumptions beyond what the physical measurements already show. The trajectories described here are not worst-case scenarios engineered to alarm. They are the central projections derived from the data available now, with the understanding that actual outcomes could be better or worse depending on factors including future emissions trajectories, the pace of deep Earth changes that are not fully predictable, and the effectiveness of human adaptation efforts. The reason this matters for a script focused on Earth's geophysical behavior, on rotation rates and core dynamics and magnetic fields, is that those deep geophysical changes are not separate from the surface story. They are part of the same coupled system. The inner core's behavior affects the magnetic field that shields the planet's atmosphere. The outer core's dynamics affect the rotation that synchronizes global infrastructure. The mantle's response to changing surface loads connects the ice sheets to the crustal rebound that affects coastal geography over centuries. The whole system is one system, operating from the iron center to the edge of space, and the monitoring of it is not an academic exercise. It is the act of paying attention to a planet in motion with enough precision and enough breadth of measurement to see the motion clearly, to understand its mechanisms, and to give human civilization the most accurate possible picture of the physical world it is making decisions about every day. That monitoring is not uniformly distributed. Some regions of Earth's surface are far better monitored than others. Seismic networks in the United States, Europe, Japan, and Australia are dense enough to support high-resolution studies of the deep Earth. In large parts of Africa, South America, and Central Asia, seismic station coverage is thin enough that significant deep Earth events could occur without being detected with the same precision. The global gravity field measurements from GRACEFO cover the whole planet, but the processing of those measurements into usable geophysical products requires significant computational infrastructure and expertise that is not uniformly available worldwide. The VLBI network that precisely measures Earth's rotation has stations on every continent, but the distribution is weighted toward the Northern Hemisphere and toward countries with significant investment in geodetic infrastructure. Expanding the monitoring network, improving its geographic coverage, maintaining its continuity, and ensuring that the data it produces is processed and made available to the global scientific community are all investments that return value across every application that depends on understanding Earth's geophysical behavior. The total cost of the entire global Earth monitoring infrastructure across all agencies and all countries is a small fraction of the cost of a single major infrastructure failure caused by inadequate understanding of the physical environment. The return on investment is not hypothetical. There is another dimension of the monitoring picture that deserves direct acknowledgement, which is the role of the international scientific cooperation that makes it possible. The measurements described throughout this script were not produced by any single country or any single institution. They are the product of a genuinely global scientific enterprise in which data from instruments operated by dozens of national agencies and international bodies flows through shared processing pipelines into jointly published results, reviewed by researchers from multiple countries operating under the shared standards of international peer review. The IERS, the International Earth Rotation and Reference Systems Service, coordinates the global network of geodetic observations that underpin all precision timekeeping and navigation. It operates through the cooperation of contributing institutions in Europe, the Americas, Asia, Australia, and beyond. The GRACEFO mission is a collaboration between NASA and the German Research Centre for Geosciences. The Swarm Magnetic Field mission is operated by the European Space Agency, with contributions from scientific teams across multiple countries. The Global Seismic Network includes stations operated by the US Geological Survey, national geological surveys of dozens of countries, universities, and international research programs. This cooperation is not automatic. It requires continuous diplomatic and institutional maintenance. It requires shared funding commitments. It requires agreements about data sharing standards, satellite frequency allocations, and the coordination of ground-based infrastructure across national jurisdictions. When international scientific cooperation is strained by geopolitical tensions, the first thing to feel the effect is often the shared monitoring infrastructure that depends on it. The geodetic satellite operations that measure Earth's rotation require coordinated tracking from stations on every continent. The seismic monitoring of deep Earth processes benefits from global station distribution. The Ocean Observation System requires ships and research stations in waters under the jurisdiction of dozens of different countries. Maintaining the scientific infrastructure that produces the knowledge described throughout this script is not separate from geopolitical questions about international cooperation. It is a direct beneficiary or casualty of how those questions are resolved. This is worth naming explicitly because the value of the monitoring is often invisible right up until it fails to prevent something that adequate monitoring would have provided warning for. The history of planetary science is not short of examples where inadequate monitoring resulted in surprises that better monitoring would have caught earlier. The 2004 Indian Ocean tsunami, which killed roughly 230,000 people across 14 countries, struck a region where the ocean-wide tsunami early warning system that would have provided adequate warning did not yet exist. After the disaster, the system was built. The detection capability was there before the event. What was missing was the distribution of sensors and the coordination infrastructure to turn detections into timely warnings for populated coastlines. The monitoring investment that would have saved hundreds of thousands of lives was cheaper by orders of magnitude than the cost of the disaster it failed to prevent. The geophysical changes described throughout this script are not operating on the timescale of a sudden tsunami. They are slower, they give more time for response. But the warning infrastructure for them and the institutional translation of warning data into planning responses is in many ways less developed than the tsunami warning system that was built after 2004. For the specific risk of a major geomagnetic storm causing widespread power grid failure, the monitoring exists, the risk assessment has been done, the protective measures are known. The implementation is incomplete. For the specific risk of a negative leap second causing networked system failures, the monitoring exists. The technical solution has been designed. The international coordination to implement it is unfinished. For the specific risk of ice sheet dynamics producing sea level rise faster than current projections, monitoring improvements are ongoing and the trajectory is becoming clearer. The planning standards that need to change to account for it are in most jurisdictions still calibrated to historical baselines. In each case, the gap is not between ignorance and knowledge. The knowledge exists. The gap is between knowledge and action, between understanding and implementation. That gap is a governance and prioritization problem more than a scientific problem at this point. And it is the problem that the existence of detailed scientific knowledge places most urgently on the agenda of institutions that make decisions about infrastructure, planning, and risk management. The scientists who produce the measurements described throughout this script cannot force that translation from knowledge to action. Their role is to produce and communicate the knowledge as clearly and accurately as possible. The translation requires institutions, policy processes, engineering standards bodies, and ultimately the public understanding that creates the political environment in which institutions act. Which brings the story back to where it began, with the fact that something changed about the planet you are standing on. Not in a way you can feel, not in a way that changes your day in any immediate and obvious sense. The ground beneath your feet feels exactly as solid as it did before you knew any of this. The sun rises and sets on a schedule that differs from last year's by a fraction of a millisecond that no human nervous system could register. The magnetic field that threads through your body and through the buildings and vehicles around you is shifted from where it was a decade ago by an amount that no compass you own is sensitive enough to show. The ice that is redistributing itself across the planet is doing so on timescales that feel geological from inside a single human life. The outer core of liquid iron churning thousands of miles below your feet has been doing what it does since the planet was young. What is different is not the planet, it is what we know about the planet. And what we know is this: the geophysical systems that constitute Earth's coupled interior and surface environment are moving simultaneously away from the baselines that defined the conditions in which every element of modern civilization was constructed. They are moving at rates and in directions that are measurable with precision and are being measured continuously by instruments that have never been better. They are moving in patterns that suggest a shared excitation rather than independent coincidence. And they are moving toward a new equilibrium that will not be identical to the one they are leaving, on a timeline that the best current science cannot yet define with the precision that the decisions depending on it require. The planet is not broken. The planet is not dying. It is doing what planets do over geological time. It is changing. The only question that remains open in any human sense is whether the civilization that happens to be living on it during this particular window of change will pay close enough attention to the measurements being made of that change too, make the decisions that the measurements indicate are necessary before the cost of not having made them arrives in the form of failures in the systems that sustain modern life. The instruments are running, the data is coming in, the picture is forming one measurement at a time from facilities scattered across every continent and in orbit above every ocean, and the planet beneath all of it is rotating on its axis, a fraction of a millisecond faster today than the models built 50 years ago would have predicted, carrying every person alive on its surface through space at a speed no human being can feel, and at a rate that has shifted in ways that every atomic clock on Earth is recording right now, in real time, without pause. That shift is not a headline. It is not a crisis packaged for consumption. It is a measurement, a datum, a data point in a record that will be studied by researchers decades from now who will look back at this particular window in Earth's history and see, in the convergence of signals across rotating systems, and magnetic systems, and ice systems, and ocean systems, the moment when the geophysical transition became visible to the civilization living through it. What they conclude about how that civilization responded is the part of this story that is still being written, not in any single laboratory or any single policy chamber or any single decision about infrastructure or standards or funding. In all of them simultaneously, just as the planet itself speaks not through any single system, but through the convergence of all its systems at once. The days are shorter, the poles have moved, the field is weakening, the ice is redistributing, the ocean is slowing, the core is oscillating, the instruments are watching, and the planet, as it has for 4.5 billion years, is continuing to do exactly what it has always done, change. The only new element in this iteration of planetary change is the civilization riding the surface of it, aware for the first time in Earth's history that the change is happening, capable for the first time of measuring it precisely, and faced for the first time with the question of what to do with that knowledge before the consequences of not acting on it accumulate beyond the capacity to manage them. That question is not answered by the data alone. Data illuminates the physical world. Decisions about how to respond to the physical world belong to the people living in it. The quality of those decisions depends on how clearly the physical world is understood, and the clarity of that understanding depends on the willingness to look honestly at what the measurements show, without filtering them through the preference for either alarm or reassurance that makes the honest picture harder to hold. The honest picture is this: Earth is a dynamic planet in an active phase of geophysical change across multiple coupled systems simultaneously. The changes are real, the measurements are solid. The mechanisms are understood at a level sufficient to project directions, if not precise magnitudes. The implications for the infrastructure of modern civilization are significant and are already beginning to manifest in the form of engineering challenges, planning gaps, and operational pressures on systems built for different physical conditions. The responses that are needed are technically known in most cases. The barriers to implementing them are primarily institutional and political rather than scientific or engineering. And The window in which those responses can be implemented most effectively at lowest cost is not unlimited. It is defined by the rates at which the physical changes are proceeding and the lead times required for the infrastructure adaptations that those changes demand. That is the honest picture, not catastrophe, not dismissal. The real, measured, verified, published, replicated picture of a planet in motion that the instruments are drawing one data point at a time, and that the civilization living on it is only beginning to see clearly enough to act on. The rotation of the Earth is telling us something. The magnetic field is telling us something. The ice is telling us something. The ocean circulation is telling us something. The seismic waves travelling through the deep interior are telling us something. Every one of these signals is a message from the planet about the state of its coupled systems. The instruments to receive those messages exist. The scientists to interpret them exist. The knowledge to act on them exists. What remains is the choice to listen.